In this presentation, we will discuss the findings of our report and outline the concrete structure of Kodi, an open-source multimedia player. In our previous conceptual architecture report, Kodi's layered architectural style was identified. This report uses Understand to analyze Kodi's source code, determining the suitability of the layered style. Our findings led to a revision of the conceptual architecture, the creation of a new concrete architecture, and the discussion of the differences. Determining the derivation process for sorting Kodi's source code efficiently was crucial. The process involved us sorting the top-level files and folders based on their names, headers, and functionality. We then aligned the components with the conceptual architecture. We posed questions to ourselves such as, what is this file importing? What class is it in? Are there any comments? Before doing further research, including looking into the file's GitHub commit history or any pull requests associated with it. Upon revisiting unsorted source code, commonalities emerged such as multiple components addressing threads, locks, and race conditions, prompting the creation of a new component. In our conceptual architecture revision, we identified areas for improvement in the Kodi source code organization. The following is a summary of the key changes we made. Firstly, we recognized the need for a common utilities component to handle various functionalities. We positioned this component in the business layer as it addresses the concurrent threading, library loading, speech integration, power settings, input handling, event handling, and display settings. Within the addition of the application settings component, it contains code that determines how the application works for each user on a single Kodi program. The translation and audio manager components were merged into the new application settings component to allow better integration. The media player component contains general files utilized by different media types, such as games, music, and video. The GUI settings component oversees Kodi's visual appearance, including UI elements, context menus, images, and styling. Within our revision, it absorbed the Font Style Manager component for unified control over text appearance. In addition to the creation of new components, we addressed inconsistencies in component descriptions, making them less user-focused and more abstract. We also eliminated Audio Manager and Translator components as they were too specific and had no corresponding source code, and we also generalized their functionalities into the newly created Application Settings component. To give a brief overview of our new concrete architecture and how each component interacts, the presentation layer consists of the user interface component, which is responsible for the user interaction, rendering visual components like buttons and text, the GUI display manager component, which acts as a bridge between the OS and the UI, managing window display for Kodi's multimedia player, and the GUI settings component, which handles the overall UI appearance. The business layer consists of the application settings component, which personalizes the user experience, the common utilities component, which facilitates efficient cross-platform operation, the player component, which manages playback systems and user interactions, the media player component, which focuses on processing, preparing, and presenting data for different media types, the add-on manager component, which manages third-party add-ons fostering Kodi's evolvability through continuous feature iteration, and finally the web server manager component, which enables remote access to media content. Within the data layer, it consists of the metadata component that manages additional information about multimedia content, the content manager component that organizes media sources and facilitates user access, and lastly, the content displayer component, which manages how the multimedia content is displayed. The concrete architecture ended up having far more dependencies than there was outlined in our first report. Here is a summary of the rationale of our largest and most significant new dependencies. Within the two-way dependency between the player component and the content manager component, we found that the AirPlay server file in the content manager calls file item from the player component for AirPlay streams. Our rationale for this was that the deviation from our conceptual architecture is that the AirPlay server was expected externally and not in the content manager. Additionally, we found that there is a one-way dependency on the web server manager for add-on GUI windows. The deviation from our conceptual architecture was that the UI was anticipated to provide this information, however, the web server manager held the necessary formatted structure. We also found that there was a two-way dependency between the user interface component and the content manager component. The content manager component prepares the KaiToast notifications, which are sent directly to the users via the UI. These were unforeseen system notifications in our conceptual architecture for the user communication. Within the new two-way dependency between the content displayer component and the user interface component, we found that the UI calls the date and time data from the content displayer and vice versa for progress bar display. There were unexpected cross-layer dependencies, such as the UI using data from the data layer without the business layer processing. Finally, the GUI display manager handles peripheral inputs requiring the player component to check the screen activity. There is an interlayer dependency which we did not account for, in that the player component ensures active screen mode for the GUI display manager inputs. In the common utilities component, there were various files that managed threading and mutex locking for concurrent processes within Kodi. This crucial functionality allows multiple dependencies of different media types to be processed simultaneously before display. Additionally, the component ensures the background processes run continuously to maintain up-to-date global variables and settings, preventing race conditions that could lead to incorrect values, vulnerabilities, or system crashes without these systems in place. For our chosen second-level subsystem, we chose the player component to analyze. The player component manages playback features, allowing user interaction, and comprises of three subsystems: the media controller, user interaction, and content handler subsystems. Employing an implicit invocation architectural style, subsystems communicate through event announcements, enhancing Kodi's modularity. The media controller subsystem controls multimedia content responding to user interaction requests for play, pause, fast forward, and volume adjustments, as well as utilizes the content handler to retrieve data and notifies other subsystems of playback status changes. The user interaction subsystem facilitates the user interaction, receiving input for playback control and translating it into requests. It also announces changes to the user interactions to the media controller and updates the relevant information through the content handler. The content handler subsystem serves as the interface between the business layer and the player component. It retrieves and stores multimedia content data, including playback history and video settings. Within our concrete architecture of the playlist component, we decided to make the addition of a playlist handler subsystem in order to orchestrate the queuing of diverse file types. The added playlist manager component empowers users for seamless playlist creation and modification, ensuring real-time data synchronization. From here, we found unexpected dependencies that differ from our conceptual architecture. The playlist manager component and the content handler component exhibit a reciprocal dependency, with the former relying on the functionalities of the latter for playlist creation and identification. This bidirectional interaction involves the use of the cFileItem class during playlist creation. The user interaction component initiates interaction with the playlist manager component through the playlist player file, utilizing a messaging system for real-time playlist updates and dynamic changes. The media controller component engages with the playlist handler component through the playlist player file, utilizing a messaging system for playlist updates and user actions, actively overseeing playlists and initiating playback. Kodi utilizes a vast library of add-ons, including those for media and player interfaces. To ensure the validity of the player interface add-ons before loading, the software checks the add-on's ID, version, and enabled status. The validation process involves user interaction subcomponent of the player component, serving as the interface between the users and the player component in the business layer. This component queries the Common Utilities Manager component in the data layer for relevant add-on manager data, using it to request the add-on manager component in the business layer for the add-on state and version information. This verification process, vital for the player's interface add-ons, reflects a broader approach applied across various areas where Kodi supports add-ons. Kodi serves as a comprehensive media library, allowing users to upload, display, and browse their files. This functionality, demonstrated through the example of loading local thumbnail files, is crucial in this aspect. The user interaction subcomponent of the player component, serving as the interface between the user and the player component, initiates the process. The content handler checks the validity of the path, and based on the response, requests the folder or file name. Verification with the Common Utilities Manager determines the existence of file utilities, facilitating further process of the data. The main challenge in this report's creation was coordinating access to the concrete architecture on the Understand software. Initially assigned to 3 members for quick transfer to the team, it was later discovered that no seamless transfer method existed, requiring manual transfers. This hindered our progress and contradicted the initial task division intent. In conclusion, our report has detailed the evolution from conceptual to concrete architecture in Kodi's software. Addressing previous limitations, the revised conceptual architecture introduced components for better alignment with the concrete architecture. The reflection analyses revealed unexpected dependencies, underscoring the complexity of inter-layer interactions that were not initially considered. The exploration of the player component illuminated architectural styles and interactions, showcasing Kodi's modularity. Our next focus will involve proposing new features or enhancements to optimize Kodi's performance and functionality.